Hi everybody, we are in section 8.5, so we're going to continue our conversation on the calculus of functions of several variables. So last time we looked at the partial derivative, how we compute a partial derivative, right, kind of what it means interpretation-wise, and now we're going to start looking at critical points and optimization. So this is something we looked at back with functions of a single variable, but now we're going to extend our arguments for maximizing and minimizing to functions of multiple variables. So, for a function f defined on a domain R, we say that f has a local blank at p naught if f of p naught is greater than or equal to f of p for all points p near p naught. So, if we're saying that the function value at p naught is bigger than everything else around it, then this is going to be a local maximum. Okay. And similarly, if we have it at p naught where f of p naught is less than f of p for everything around p naught, then that tells us that f has a local minimum at p naught. Alright, so we have our local max and local min. And so these are defined the same way that they were for functions of single variables. The difference is just now we're working with x's and y's as inputs and working with a third value as an output. We say f has a global maximum if f of p naught is greater than or equal to f of p for all points p in the region. Okay, so if f of p naught is bigger than everything else on the entire function, that's a global maximum. And if the function value, that one should be less than or equal to, let me fix that, sorry. So that one should be less than or equal to there we go. So, here we go. So if we have that, again, the output at p naught is bigger than everything else in the entire region, then that is our global maximum or absolute maximum. And then similarly, if the output is smaller than everything else in the entire function, that is a global minimum. Alright. Okay, now how can we read this on a contour diagram? So estimate the location and value of any local maxima and minima of f of xy. Are there any global extrema in the given region? So when we're looking at this contour map here, remember that these values on the contours are telling us height values, right? Output values. So the outputs are going from 3 to 4 to 5 to 6, right? 5 to 6 to 7 to 8, down to 4 over here. So, you could try to visualize what exactly is happening on this contour diagram, right? So we've got our height of 4, height of 3 down here. We've got, height of 5, height of 6, and then try to connect the dots as smoothly as possible to get a clearer picture of what's going on, but we're not going to try to draw a bunch of these in 3D. So, but just so you get an idea of kind of what's happening. So, if we're looking for local maxes and local mins, we're looking for a point that is greater than all the points around it or smaller than all the points around it. So, the first one you might be able to key in on is going to be over here. Okay, because notice that we go from 3 to 4 to 5 to 6, and then if we kind of are in the middle of that contour, we have that's going to be the highest point, and its value is going to be somewhere above 6, right? Maybe it didn't go all the way up to 7, right? Otherwise, maybe we'd have another contour there. But we're saying that it's going to be above 6, because then when you pass it on the other side, everything outside of this point is getting lower than it. Okay, so that one we're going to say there is a local maximum at, what's that point? That is the point 2, 6. 2, 6 with value above 6. Okay. So then next up, you might notice another one standing out to you, and that's going to be over here. So notice we're going 5 to 6 to 7 to 8 as we go up this kind of slope here. And right there in the middle, looks like we're going to have another highest point, all right, with a value that's above 8. All right, so hopefully visualizing that is okay for you guys. So we're also going to have a local maximum at the point, let's see, what point is that? That is the point 6, 5 with value above 8. Right, because it probably doesn't go all the way up to 9, otherwise we'd have another contour there inside of 8. But it looks like it would go above 8 at least. Okay. And then if you can notice, there is one more on here, and that's going to be somewhere in here. Somewhere inside of that 3 contour, because notice again we're going downward from 6 to 5 to 4, right, downward, downward, downward. But then once we get somewhere in here, and then we move out, now we're going up again, right, up towards that 4 contour here, from 3 to 4. So that tells us that somewhere inside of that kind of elliptical contour at 3, we're going to have a minimum value, right? Because it's going to be smaller than 3, because as you move out of there, you're moving up in all directions. Okay, so where that point is, we can just go to the nearest one. That's kind of in the middle, at the point 3, 2. Okay, so we can go ahead and say we have a local minimum at the point 3, 2 with value below 3. So again, we're below that contour at 3. Alright, so that's kind of how we're reading these. It also asks, are there any global extrema? Well, the global extrema would just come from those local extrema, right? So which one is the absolute highest point in the entire region, and which one is the absolute lowest point? And that would be the highest value is above 8, that'd be right there. Lowest value is below 3, right there. So it looks like we have a global max at 6, 5 and a global min at 3, 2. Yeah, at least on this region. So, alright, so we can read and interpret these from graphs, from contour diagrams, but we also want to be able to determine these maximum and minimum values analytically or algebraically, right, from a function. So this is going to bring us into that next part. So if a function f of xy has a local maximum or minimum at a point x0, y0, not on the boundary of the domain of f, then either fx, so the partial with respect to x, is 0 and the partial derivative with respect to y is 0, or at least one partial derivative is undefined at the point x naught, y naught. Okay? So this should look similar, right, to our previous test for max and mins, right? It's where the derivative equals 0 or is undefined, but in this case there are two derivatives, right? There's the derivative with respect to x and the derivative with respect to y. So either both of those are going to be 0 or at least one of them is undefined at the point. At points where each of the partial derivatives is either 0 or undefined are called critical points. So just like we had before, okay, just now with two derivatives instead of one. Now using the critical points, we are going to be able to test them, but we have one test that we're going to use for functions of several variables, and that is the second derivative test. So it's not the same test as what we had before. This one is a little more formulaic. So here we have, suppose that x naught, y naught is a critical point where both partial derivatives are equal to 0. And then here's our formula. So let d equal fxx, so that's the second derivative with respect to x twice, times fyy, okay, so second partial derivative with respect to y, minus fxy squared, okay, so partial with respect to x and then y, and then square that value. Okay, that's the value of what we call d. Okay, this is also called the d test, in addition to the second derivative test. Okay, so that's the test we're going to use. And this one, the reason that we are able to just square fxy is because if you remember from the last section, we have for any continuous functions, fxy equals fyx. So you don't have to go to the trouble of finding both of those. Instead, you can just get one of them and square it. Okay. Now, what this calculation does is it's going to give us a result for d that's going to tell us what we need to know about the function. So, here we have our different cases. If d is positive and fxx is also positive, then f has a local minimum at the point. Okay. If d is positive and fxx is negative at the point, then f has a local maximum at the point, x naught, y naught. Okay. So this is the first thing to notice here. These both have the condition that d is positive. So if d is positive, that tells you that it's going to have either a max or a min. It's definitely going to have one of those. And then which one it is depends on what the value of fxx is. Okay, that second derivative. Think of this like the second derivative test for a single variable, right? The second derivative test tells us if it's concave up or concave down. This does something similar to that, except we're looking at, right, a 3D shape. So it's telling us whether it's opening upward, opening downward, like that. So it does, in essence, it does the same thing. Okay, so it's just telling us we know that it's either a max or a min. So now, which is it? Okay, so that's if d is positive. If d is negative, then f has a what we call a saddle point at x naught, y naught. This is a special type of point that I'll talk about in just a second. And then if d equals 0, so the last possible outcome, we say the test is inconclusive. So it doesn't give us any usable result. So that just means we are hoping that we never get d equal to 0, because then we can't use this test. Alright, so we know that if d is positive, we have either a max or a min, and we check fxx to determine which it is. If d is negative, we have a saddle point, and if d is 0, the test is inconclusive. So now, what is a saddle point? Well, a saddle point is neither a max nor a min. Okay, so in terms of calculation-wise, that's really all you need to know. Let me show you what a saddle point would look like. We actually saw an example of one before, I just didn't call it this yet. So if you had, right? There's x and y. So remember we had a graph that looked kind of like this, kind of rainbows on all sides, right? And we had, this was, right, 300, 500, 600, 800, right, 500, 300, 700, 800. You can go back and find that graph again. And I did give you a rough sketch of this before, but let me just give you another one now so you can see what I'm talking about in this context. Hopefully I can make this work. Yeah, that's pretty good. And there along the back side. There, something like that. That's roughly what that contour diagram would look like in 3D. Notice that this looks like a saddle, right? Like a saddle you would ride like on a horse or something. The saddle point is going to be right in the middle of all of this. Okay, so that's going to be our saddle point. The reason that we say saddle point is neither a max nor a min is because when you're looking at it from different perspectives, it looks like something different. So if we were going, so let's look back at this graph. So if the saddle point is right here, and I'm looking strictly in the x direction, as I go left and right, my values are getting larger, right? I'm going up to 700 to 800, etc., and 600, 800, etc. So in that case, it would look like a min, right? Because it's smaller than everything in the x direction. But if I go in the y direction, I go down 500, 300, etc., and then same thing, down 500, 300. So in that case, it would look like a max in the y direction. And because it has this relationship, it looks like a saddle, and we consider it neither a max nor a min because it doesn't satisfy the requirements. So, right, if I'm going in the x direction, we have what looks like a min, but in the y direction, we have what looks like a max. Okay, so it is in fact neither a max nor a min. So that is what a saddle point looks like. Okay, and we don't really need to know too much more beyond that of what a saddle point is, just so you have just a basic understanding of what it tells us. Okay. So let's look at an example. So find any local maxima, local minima, and saddle points of this function. So to do this, we need to first find the critical points, and once we have the critical points, then we test them using that second derivative test. So let's go ahead and get the critical points. So we need to get the partial derivatives. Okay, so fx of xy and fy of xy. Okay, so this is our function in question here. So fx is going to be derivative with respect to x. So that's 2x minus 2 plus 0 minus 0 plus 0. Because again, none of those have x's in them. So their partial derivative with respect to x is the variable, those are all zeros. So this is just 2x minus 2. And fy, so derivative with respect to y, 0, 0, 2y minus 4 plus 0. So just 2y minus 4. Alright, and then we set both of those equal to 0 and solve for the corresponding values. This first one gives us x equals 1. The next one gives us y equals 2. So this tells us we have one critical point with x coordinate 1, y coordinate 2. Oops. So at the point 1, 2. All right. So we got the critical point. So now we need to test it. Alright, so in order to do that, we're going to need to get all of the second order partials, or at least 3 of them. So fxx, so that's the partial derivative of fx, again, with respect to x. So that's this one. Derivative of that with respect to x is just 2. So that's 2. Fyy. So again, partial of fy again with respect to y is also 2. And fxy, so partial with respect to x, and then partial of that with respect to y. There are no y's in this function at all, so that's just going to be 0. Okay, so once we have those, now we go ahead and plug in to the d value. So that's fxx at the point 1, 2 times fyy at the point 1, 2 minus fxy at the point 1, 2 squared. So that's 2 times 2 minus 0 squared, which is just 4, which is greater than 0. Okay, so if you look at the top of your page, right, so we got d is greater than 0, so that tells us that there must be either a max or a min, but we don't know which one yet. Okay, so d is greater than 0, and to determine which it is, we look at fxx at 1, 2, right, that's 2, which is also positive. So if d is positive and fxx is positive, that means we have a local minimum. Okay. Thus, f has a local minimum at the point 1, 2. And if you wanted to actually find the value, you could just plug the point 1, 2 into the original function to get its output. So to get f of 1, 2, and that value is actually 0. Okay, so that gives us our local min and the output value from that local min. Alright. So now we have a bit more of an application example. So a manufacturing company produces 2 products which are sold in 2 separate markets. The company's economists analyze the 2 markets and determine the quantities Q1 and Q2 demanded by consumers at the prices P1 and P2 of each item are related by these given equations. The company's total production cost is given by that function for C. If the company wants to maximize its total profits, how much of each product should it produce, and what is that maximum profit? Okay, so there's a lot going on here, but what we have here, the quantities demanded give us these 2 equations, okay, that relate P1 and Q1 and P2 and Q2, and then their cost is given by this function, so we're going to need that. And if they want to maximize total profits, how much should they produce? Okay, so we're trying to determine profit here. Hopefully everybody remembers what profit is. That's going to be revenue minus cost. We've been given no formula for revenue here, so we need to go ahead and create it for ourselves. Okay, so to get total revenue, that's going to be, so revenue, remember revenue is price times quantity, P times Q, but we have 2 separate products here, so this is going to be price times quantity for the first one, plus price times quantity for the second one. So P1 Q1 plus P2 Q2. And we have those from this expression here. All right, so we can write those exclusively in terms of Q1 and Q2. So that's going to be, so P1 is 600 minus 0.3 Q1 times Q1 plus P2 is 500 minus 0.2 Q2 times Q2. Okay, and then solve that out, right? So distribute, we get 600 Q1 minus 0.3 Q1 squared plus 500 Q2 minus 0.2 Q2 squared. So that's going to be our total revenue. So to get profit, that's which we represent with pi, right? So we don't get it confused with P for price. Profit is revenue minus cost. And if you go ahead, and I'm going to kind of jump past some of this work here, but if you take this function minus this one, okay, combine any like terms that you can, which there will be a couple, then write them all out. I'm going to just show you what we get here. So this is going to give us negative 16 plus 598.8 Q1 minus 0.3 Q1 squared plus 498.5 Q2 minus 0.2 Q2 squared minus 0.2 Q1 Q2. Okay, so we get this long, crazy expression for profit. Okay, but mathematically it doesn't take much to get there. Okay, it's just subtracting a couple terms. And now, if we want to determine the values that will maximize profit, then we need to get any critical points that will occur. So in order to do that, we need to take some partial derivatives. So I'm going to need to take the partial derivative of that profit function with respect to Q1 and Q2. So I'm going to write this using my partial notation. So that's partial derivative of profit with respect to Q1, and then partial derivative of profit with respect to Q2, that second quantity. So take the partial derivatives of this. So with respect to Q1, we're going to be left with 598.8 minus 0.6 Q1 minus 0.2 Q2. And partial with respect to Q2, that's going to be 498.5 minus 0.4 Q2 minus 0.2 Q1. You set these both equal to 0. You're going to have two equations there with two variables. You can solve those. For Q1 and Q2, you can use either the method of substitution or elimination. Okay, remember those from algebra. So use those, solve for Q1, solve for Q2. I'll just show you, kind of cut to the punchline here. So solve to get the following values. We get Q1 is 699.1 and Q2 is 896.7. So these points here comprise of our critical point. Right? If you wrote it as an ordered pair, that would be like our critical point. Which means now we're going to need to test this point. Okay, so for our test, we're going to need to get the second order partial derivatives. So we're going to need second partial of profit with respect to Q1 squared. Okay, so just mixing up the notation so you guys can get comfortable with both. We have partial derivative of profit, second order partial derivative with respect to Q2, and then second partial derivative of Q with respect to Q1 and Q2. Alright, so notationally this would be the same as writing, profit sub Q1. This would be, like f sub x, kind of like we had before, right? Fx or Fy, and I guess there would be two of those, right? Second order partial, and then Q1, Q2. Okay, so it would be equivalent to writing it like that. But when we're dealing with variables that aren't x and y, typically we like to use the partial notation like this. Okay, so get those second order partials. Those again take the partials of those again. So then this gives us negative 0.6. With respect to Q2, we get negative 0.4. With respect to Q1 and then Q2, we get negative 0.2. So then we go ahead and plug those values into the function d. So that's going to be negative 0.6 times negative 0.4 minus negative 0.2 squared. Which, if you run those numbers, you get 0.2, which is positive. Okay, so the fact that we got a positive value for d tells us that there is either a max or a min, but we don't know which one yet. So then we look at the equivalent of fxx, so that's just the second order partial for the first variable, so that's second order partial with respect to Q1 in this case. That one was negative 0.6, so that's less than 0. So if we got that d is positive, that means there's either a max or a min, and the fact that that second order partial was negative tells us that it must be a maximum, right? Which is what we wanted. We wanted to maximize profit. So, excuse me. So thus, profit is maximized when producing about 699 units of the first product, right? Because that was the first critical point that we had here up here for Q1 was 699.1 of the first product, and 897 units of the second product. Okay, so that's when we get our maximum profit occurring, is when they produce about 699 units of the first product and 897 units of the second product. Okay, so that's when we maximize profit. But then it asks, what is the maximum profit? Well, to get that, you take those numbers for Q1 and Q2 and plug them into the profit function. So you would just plug them into here. Okay, which obviously that would get pretty messy, but that's okay because we're just doing this one together. So let me just tell you what you would get out of that. Okay, the maximum profit is about $432,797.02. Alright, so if you take those values that we found that maximize that profit function, and then actually plug them into the profit function, and then that'll give you what the actual maximum profit would be. So, alright, so that brings us to the end of section 8.5. When we come back with 8.6,